Okay, this is a recording for the review for exam 3, exponentials and logarithms. First 4 questions are graphs. First 2 are exponential graphs. They come from section 5.1, graphing exponentials. Questions 3 and 4 come from section 5.2, graphing logarithmic functions. On questions 1 and 2, exponential graphs really have 2 characteristics that you need to find in order to graph. First is the horizontal asymptote, and that's located by using this number here. This represents a vertical transformation down 1 unit. So the horizontal asymptote is located at -1 on the y-axis. The y-intercept can be found by letting x equal 0. Well, let x equals 0, we have 3 to the -1, which is 1/3. And we have to subtract 1 from that. And 1 is 3/3. 1/3 minus 3/3 is -2/3. What you write about there? If we let x equal 1, 1 minus 1 is 0, 3 to the 0 is 1, 1 minus 1 is 0, and if we let x equal 2, 2 minus 1 is 1, 3 to the 1 is 3, minus 1 is 2. This is an example of an exponential growth function. Okay, right here on question 2, because the base is less than 1, still greater than 0, this is going to be an exponential decay graph. It's graphed the same way. We want to locate the horizontal asymptote, which, because of the -1, has been moved down 1 unit. If we want to find the y-intercept, we can let x equal 0. 0 minus 1, or sorry, 0 minus 2 is -2. 1/3 to the -2 minus 1. 1/3 to the -2 is the same as 3 squared, which is 9. 9 minus 1 is 8. And because this is an exponential decay graph, the shape's going to be, from left to right, the shape's going to be decreasing. The graph's going to be getting closer to this horizontal asymptote. So, let x equal +1. 1 minus 2 is -1. 1/3 to the -1 is 3. 3 minus 1 is 2. And if x equals 2, 2 minus 2 is 0, 1/3 to the 0 is 1, 1 minus 1 is 0. Logarithmic graphs have similar characteristics because they're the inverse of exponential. We're going to locate the vertical asymptote, which is found by the transformations inside the function. X plus 1 is a shift to the left 1 unit. That also shifts the vertical asymptote to the left. Now we need to find a couple of points on the graph. We have to choose values of x that are in the domain. The domain of this function is from -1 to infinity, not including -1. Because you can't take a logarithm of 0. So if we let x equals 0, for example, then 0 plus 1 is 1. The log of any base of 1 is 0. 0 minus 1 is negative 1, so 0. Comma negative 1 is a point on the graph. If we are a little bit clever now about our x values, we could let x equal 2, for example, because 2 plus 1 is 3. Log base 3 of 3 is 1. 1 minus 1 is 0. And we want one more number for x such that when you add 1 to it, it becomes a power of 3. So that could be 8. 8 plus 1 is 9. Log base 3 of 9 is 2. 2 minus 1 is 1. So 8 comma 1. Now this transformation here is a transformation 2 units to the right. So the vertical asymptote is located right there. The domain of this graph, or of this function, is from 2 to infinity, not including 2. So we can only choose x values that are in the domain. So we could choose a 3. 3 minus 2 is 1. Log base 2 of 1 is 0. 0 minus 2 is negative 2. So 3 comma negative 2 is on the graph. We could choose a 4 for x. 4 minus 2 is 2. Log base 2 of 2 is 1. 1 minus 2 is negative 1. And then we could choose another value of x such that when you subtract 2 from it, you get a power of 2. So that could be a 6. 6 minus 2 is 4. Log base 2 of 4 is 2. 2 minus 2 is 0. And there's that graph. Okay, next section is just rewriting logarithmic equations in the exponential form. So to get rid of a logarithm with a base of 6, you use a base of 6 on both sides. That cancels out, so you have 216 equals 6 to the third. Over here, to get rid of a log base 9, you use a base of 9 on both sides. Those cancel out, so you have 81 is equal to 9 squared. Alright, question 7. To get rid of a log base 13, use a base of 13. So 1 is equal to 13 to the 0. And number 8, to get rid of a natural log, you have to use a base of e. You have 155. So e to the power of x. Okay. These next 4 go in the other direction. Now they're in exponential form. You have to rewrite them in logarithmic form. So we need to cancel the base of the 2. Means we have to use a log base 2 on both sides. So if we use a log base 2 over here, it's going to cancel 2, leaving a 6. If we use a log base 2 on the right side, we have log base 2 of 64. On number 10, if we want to cancel the base of e, we have to use a natural log. Natural log of e to the x is x. Over here, we're going to get the natural log of 216. Question 11, we have to take log base 289 on both sides. So we have to take log base 289 of the left side. 289 will cancel, leaving 1/2. On the right side, we'd have log base 289 of 17. Question 12, log base 8 of 8 to the 2/3 is 2/3. And then take a log base 8 on the right side, and we get log base 8 of 4. Evaluate each expression. The log of any base of 1 is always equal to 0. On number 14, log base 16 of 4, you can rewrite 4 as 16 to the 1/2. The power of 1/2 just means square root, and the square root of 16 is equal to 4. So these two are equal to each other. Because these have matching bases, we have a log base 16, and here we have a base of 16. Those are going to cancel. So the answer is 1/2. Okay, log base 5 of 125. 125 can be written as 5 to the 3rd. Now that they have matching bases, those logarithms cancel. The answer is 3. Number 16, similar to number 14, the 5 can be written as 25 to the 1/2. Now that these have matching bases, the log base 25 cancels the base of 25, leaving 1/2. Number 17, log base 3 is an exponent with a base of 3. Those are inverses of each other, so those cancel out, leaving an 8. Natural log cancels out a base of e, so the answer is 5. Okay, number 19, we can use, it says use properties of logarithms to solve. What that means is just rewrite these in exponential form. If we want to get rid of a log base 12, we use a base of 12 on both sides. Those are gone. X equals 12 squared, which means x equals 144. Our number is 20. Use a base of 6 on both sides. X equals 6 to the negative 1, which is 1/6. Number 21 is a base of 4 on both sides, so x equals 4 squared, which is 16. And on number 22, let's use a base of x on both sides. If 3 is equal to x to the 1/3. Now x is being raised to the 1/3 power, so we can raise it to the 3rd power. We have a power raised to a power, let's multiply. 1/3 times 3 cancel each other out to 1. So x is equal to 3 to the 3rd, which is 27. Okay. Number 23, when you're condensing into a single logarithm, you want to start with numbers in front of logarithms like this 5. This is an exponent. It's really a z to the 5th. This one's a little tricky to see, the last part, 23. But you can think of it this way: log base 4 of y. Now I'm going to move this 5 back up as an exponent on top of z, so it's going to be log base 4 of z to the 5th. Now this you can think of as 1/3 times the log. You can think of that as 1/3 times the log of x, rather than the log of x divided by, alright, it's got a base of 4, rather than the log base 4 of x all divided by 3. And because the 1/3 is in front, you can move that back up as an exponent. So this is going to be plus log base 4 of x to the 1/3. I'm going to take these two logarithms, the first two, because there's a plus sign between them, I'm going to condense them using the product property. So the y and the z to the 5th need to form a product. So this is going to become log base 4 of y z to the 5th plus log base 4 of x to the 1/3. Now to condense these two logarithms, there's a plus sign between them as well, which means that the expressions inside the logarithms form a product. X to the 1/3 is going to multiply y z to the 5th. So final answer here is going to be the log base 4 of the product x to the 1/3 times y times z to the 5th. Now if you wanted to write x to the 1/3 as the cube root of x, that's fine. Or if you leave it as x to the 1/3. Number 24, we're going to start by moving all of these numbers back up as exponents. We're going to have log base 4 of u to the 5th minus log base 4 of w to the 5th minus log base 4 of v to the 10th. Now, taking these first two logarithms and condensing them, because there's a minus sign between, we're going to use a quotient rule, which says that u to the 5th and w to the 5th are going to form a quotient. So this becomes log base 4 of u to the 5th over w to the 5th minus log base 4 of v to the 10th. Now we're going to combine or condense these two logarithms, and again, because there's a minus sign between them, they're going to form a quotient. U to the 5th divided by w to the 5th is going to be divided by v to the 10th. So this v to the 10th is going to appear in the denominator down here. So condensing these into a final expression, log base 4 w to the 5th over w to the 5th v to the 10th. Okay. For number 25, it's much easier to expand logarithms when you're dealing with exponents and not radicals. First thing I would do is change these radicals into exponents. So this is log base 5 of x over y to the 1/2 to the 1/2. Which, simplifying this, is log base 5 of x to 1/2 over y to the 1/4. Now we're taking the logarithm of a quotient, so when we expand that, we're going to use subtraction. So this equals log base 5 of x to 1/2 minus log base 5 of y to the 1/4. We're going to move the powers down in front of the logarithm because of the power property. So 1/2 times the log base 5 x minus 1/4 times the log base 5 of y. Now on line 26, we're going to expand the quotient using the quotient rule, meaning we're going to have to use subtraction between two logarithms. So we're going to have log base 4 of a to the 6 minus log base 4 of CB to the 3rd. But now here we're taking the logarithm of a product, so we need to expand this product using addition, keeping in mind though that we still need to subtract this entire expression, so in an expanded form it needs to be in a parenthesis. So this is going to be log base 4 a to the 6 minus, now expand the logarithm into two separate logarithms, log base 4 of c plus log base 4 b to the 3rd. Now moving exponents down to the front and distributing the minus sign to get rid of parentheses, we're going to have 6 times log base 4 of a minus log base 4 of c minus 3 times the log base 4 of b. Okay. Next section is solving logarithmic equations. The method is to isolate this logarithmic expression here so that you can use a base to get rid of the logarithm. So to isolate the logarithmic expression, we kind of divide. The reason we're dividing is because the -3 is multiplying the logarithms, we do the opposite. So the log base 2 of v minus 7 is equal to positive 3. We use a base of 2 on both sides. To cancel log base 2, we have v minus 7 is equal to 8. Adding 7 to both sides is v is equal to 15. On number 28, the logarithmic expression is already isolated. There's nothing in front of it. There's nothing outside of the function either. So we just need to cancel the logarithm. This is a natural logarithm that has a base of e. So to cancel, we use a base of e on both sides. So x minus 1 is equal to e to the 3rd. Adding 1 to both sides gives the solution x equals e to the 3rd. Plus 1. Okay. On an equation involving multiple logarithms, and this one's even a little bit different because there's logarithms on both sides. What we need to do is make one logarithmic expression on the left and one logarithmic expression on the right. So on the left we need to combine these two logarithms into one logarithm. Because there's a plus sign between them and they have the same base, we can condense them using the product property. The x is going to multiply x plus 6. So when these combine into a single logarithm, we get the log base 5. Now x times x plus 6 is x squared plus 6x. And that's equal to the log base 5 of 55. Now to get rid of logarithms with a base of 5, you have to use a base of 5. So if we use a base of 5 on both sides of the equation, those cancel each other out, and we're just left with the quadratic equation, x squared plus 6x equals 55, which means that x squared plus 6x minus 55 is equal to 0. If we factor this into x plus 11 and x minus 5 is equal to 0, we get the solutions x equals negative 11 and x equals 5. Now, we need to consider the domain of logarithms. It is impossible to take the logarithm of a negative number. If we tried to check our solutions x equals negative 11 in this logarithm or in this logarithm, you'd end up with an undefined expression. You can't take a logarithm of a negative number, so x equals negative 11 is extraneous, and the solution is x equals 5. Number 30, we have to combine these two logarithms into a single logarithmic expression. Because there's a plus sign between them, we're going to again use the product property. And then log base 9, and then 5 multiplies x plus 10 to be 5x plus 50. Now we have to use a base of 9 on both sides. So 5x plus 50 is equal to 9 squared, which is 81. Subtract 50 on both sides. We get 5x equals 31, divide by 5, and then we have x equals 31 fifths. And 31, this is an exponential equation now. To solve exponential equations, you have to use logarithms. The steps are to isolate the exponential term. This is the exponential term right here, 8 to the x. So to get rid of a base of 8 now, we use the logarithm on both sides. Log base 8, that's going to cancel that, so we have x equal to the log base 8 of 35. And because we are using calculators, we leave the answer in that form. Now in 32, we have to isolate the exponential term, which is the base and the exponent, so we need to get that by itself. 3 does not multiply the 2 and to become 6. 3 is multiplying the expression 2 to the x. So to get rid of the 3, we divide by 3. We have 2 to the x. 27 divided by 3 is 9. Now we use a log base 2 on both sides. We have x is equal to the log base 2 of 9. Number 33, e to the n minus 10 is the exponential term, so this needs to be isolated before we can get rid of the base of e. So I need to add 8 to both sides. We have e to n minus 10 is equal to 30. Now we can get rid of the base of e using a natural log. So n minus 10 is equal to the natural log of 30. Now we can add 10 and add 10. Because the 30 is inside the natural log, 10 cannot be added to 30 to make 40. So the answer is n equals natural log of 30 plus 10. For number 34, we need to isolate this expression here, 8 to the x plus 3, so we need to divide by the 8. And we have 8 to the x plus 3 is equal to 3. Now we can use a log base 8 on both sides. So we have x plus 3 is equal to the log base 8 of 3. Subtract 3 to isolate x. And again, because this 3 is inside of a logarithm, we can't subtract 3 from it. So the answer is x equals log base 8 of 3 minus 3. So on 35, this is a continuously compounded interest problem. The formula for continuously compounded interest is the future amount is equal to the principal amount times e raised to the rate times time. So the question is asking how long would it take? That's a measurement of time. So the variable we're going to be solving for is time, which means we're going to have to know a value for all the other variables. We need to know the rate, we need to know the principal investment, and we need to know the future investment. The rate is 6%, that's 0.06. Principal investment is $5,000. The future amount is going to be $10,000 because we're wanting it to double. So A is equal to 10,000, P is equal to 5,000, and the rate is equal to 0.06. So we know all of the other variables except for t, which is the one we're solving for. So 10,000 is equal to 5,000 times e to 0.06 t. Now the variable we're solving for is in an exponent, so to solve for that we need to cancel the base so that the variable is no longer an exponent. The base is e, we need to get e by itself, so we need to divide 5,000 with 2 is equal to e to the 0.06 times t. Now to cancel the base of e, we use a natural log on both sides. So we have the natural log of 2 is equal to 0.06 times t. Now t is no longer part of an exponent because the base of e is gone. 0.06 is multiplying t, so divide by 0.06. So t is equal to the natural log of 2 divided by 0.06. That's in years. Now to model an exponential situation, whether it's growth or decay, we use a formula that's pretty much the same as this formula here. The variables are just different. We have the amount at any given time t is equal to an initial amount, a sub 0, where a sub 9 times e to the k t, where k is a growth factor, similar to an interest rate in this money problem here. Now we've been given an initial count a sub 0, but we haven't been given the growth factor. We need to first solve for the growth factor to find k. Because if it wants us to find a function that models the number of bacteria at any time t, that means t can be the only unknown in the formula. So we do need to know a value of k. Now we do know that it doubles every 40 minutes. 40 minutes is a measurement of time, and doubling 10,000 would give us a future amount of 20,000 at that particular value of time. So we could say that 20,000 is equal to 10,000 times e to the k. We can plug in a 40. This is going to allow us to solve for k, which will give us a particular k value. And because k is an exponent, we have to solve and get rid of the base. So we're going to divide by 10,000. Two is equal to e to the k times 40 to the natural log on both sides. Natural log of e cancels out, so we have the natural log of 2 is equal to the k times 40 divided by 40. So we know the value of k now is equal to the natural log of 2 over 40. So now we can finish our model. We know the value of k and we know the initial amount. So the future amount at any given time t is going to equal 10,000 times e, natural log of 2 over 40 times t. What this model can now do is predict the future amount of this bacteria at any given time, t. Okay, 37 is an exponential decay situation, but it uses the same formula. The amount at any given time t is equal to the initial amount times e to the kt. So this process is exactly the same as number 36. We do know the initial amount, a sub 0, equals 200 milligrams, but we don't know the value. We don't know the value of k, so we need to use the fact that the half-life is 333 days. So if you start with 200 milligrams and allow 333 days to pass, you're going to have half of the substance remaining, which is 100. So the future amount will be 100 if you start with 200 milligrams and allow 333 days to pass. This will allow us to solve for k because k is an exponent. We need to cancel the base of e. So if we divide 200, we're going to get 1/2 equals a e to the k times 333 using natural log on both sides. We have the natural log 1/2 is equal to k times 333. So if we divide by 333, now we know the value of k is equal to the natural log 1/2 over 333. So the function now becomes the amount at any given time t is equal to the initial count, or the initial mass, which is 200 milligrams, times e, the natural log 1/2 or 333 times t. Okay, question 38 is using logarithms to evaluate the pH scale to find the acidity of solution. So there's some kind of a liquid solution here who has a hydrogen ion concentration of 4.51 times 10 to the negative 6. The pH then is the logarithm of that hydrogen ion concentration. So pH is equal to negative logarithm of 4.51 times 10 to the negative 6. Now inside this logarithm, we're taking the logarithm of a product, 4.51 times 10 to the negative 6. This is just a number in scientific notation. So if we wanted to expand to this into separate logarithms using the product property, this is going to be negative 4.51 plus log of 10 to the negative 6. If we want to distribute the minus sign now, we get negative log 4.51 minus log 10 to the negative 6. Now these are common logarithms, they have a base of 10. This log base 10 is going to cancel with that base 10, leaving a negative 6. But if you subtract a negative 6, that becomes a plus 6. So what we have now is negative log 4.51 plus 6. Now here it says log base 4 or log base 10 of 4.51 is equal or approximately equal to 0.654. So we have negative 0.654 plus 6 So if we combine these, we're going to get 5.346. That's the measurement, the approximate measurement on the pH scale. Okay, last problem here. Okay, this is using logarithms to discuss the Richter scale, which is a logarithmic scale. The magnitude of an earthquake is equal to the logarithm of the intensity of the earthquake divided by the intensity of a standard earthquake. This is the formula that was learned in section 5.5. So consider the first one that has a magnitude of 5.2. 5.2 is equal to the logarithm of the intensity of that earthquake divided by the standard intensity of an earthquake. What we need to figure out now is how much more intense an earthquake would be if it measures 7.5. So now we have 7.5 as a magnitude, and that's equal to the log. Now trying to compare this intensity to this intensity, we don't know exactly how much more intense this earthquake is going to be, so we're going to say, well, it's x times the intensity divided by s, where x is the increase in the intensity. Since we don't know how much more intense it's going to be, we're going to call it x. Now, manipulating this equation a little bit, or this expression inside of the logarithm, this could be written as log of x times I over s instead of x times I over s, because now we have a product inside of here, and we could expand the product using the product property and expand this into two logarithms. So we could have 7.5 equal to the log of x plus log of I over s. And then the reason I wanted to separate the x from the I over s, because up here we know that the log of I over s is equal to 5.2. So this logarithm right here of I over s can be replaced with 5.2. So we have 7.5 is equal to the log of x plus 5.2. Now if we subtract 5.2 on both sides, we're going to have 2.3 is equal to the log of x. Now this is log base 10, and we're solving for x. So to get rid of this logarithm that has a base of 10, we need to use a base of 10 on both sides. So x is equal to 10 raised to the power of 2.3. This is how much more intense that earthquake is, even though it only raised up 2 points on the Richter scale. The intensity increased by a magnitude of 10 to the 2 point, or by a factor of 10 to the 2.3 power. So 10 squared is 100, so this is more than 100 times as intense